So this is the problem we're going to be looking at. You could take a minute, you could pause it and write down the problem if you don't have it in your book. But it's a buffer problem. It's actually got the word buffer in it. So, okay, fine. We've got the question. Question talks about glacial acetic acid. When you see acetic acid, you should be thinking weak acid, right? That is a weak acid. So Ka should come to mind for one thing. Okay, so they give you some information. 98% acetic acid by mass. They give you a density. Question is, what volume of this stuff do you need to make a buffer with a pH of 4.20? So hopefully when you think of buffer, you kind of remember that if you have equal concentrations of a weak acid and its conjugate base, then you're going to have a situation where pH equals pKa. So we do actually know the Ka of acetic acid. They give us what the weak acid is. So let's look at what we have. Let's see. All right. So the original solution, this is the information we have. Yes, it's 98% by mass, so gram for gram. 98% by mass acetic acid. I use CH3COOH. You'll sometimes see this is C2H3O2. Doesn't matter, just make sure you're comfortable either way. We've got a density. And Ka. I underlined this in green because this is something that we looked up. You would be given this information if it were like a test question, but since you have access to your textbook, and you could just look this up. And we have, so that's a weak acid. Highlight that. We also have 100.0 milliliters of sodium hydroxide. That's our strong base. If we're going to be making a buffer, one thing to point out is that the hydroxide that was there will no longer be there after we get done. The hydroxide that was there is going to react with these protons, right? And so that's going to be consumed. Right? In our final solution, we're going to have a weak acid and a weak base, and that's it. The weak acid is the original acetic acid. The weak base is the acetate ion. So here's our Ka expression. That's very easy, right? We know the pH is 4.20. So if that's the pH, then the concentration of hydronium, or concentration of H+, is going to be 6.3 times 10 to the negative fifth. All right, so we know Ka, we looked that up. We know H+. Okay, so we know two of these things. Since we are dealing with a buffer, right? A buffer is a situation where we have a definite concentration of this and a concentration of this. We know that this is present and we know this is present. So since we have these two things, we're going to be able to get the ratio of the acetate to the acetic acid. So that's what we're looking to do. Figure out what is the ratio. Are we going to have more of this? Are we going to have more of this? What's the exact ratio going to be? One thing, if we just look at our numbers, we should know what we're actually expecting. This Ka is 1.8 times 10 to the negative fifth. The H+ concentration is 6.3 times 10 to the negative fifth. So there's actually a bit more H+ than at the Ka, right? If pH equaled pKa, then these concentrations are equal. So if we wanted a pH, I think it's about 4.74. If we wanted that pH, then those two things would be equal. We have more H+ than that. So since we have more H+, we are going to expect that we're going to have more acetic acid than acetate in this final solution. So that's just some way to think about the calculation that you're doing and know what you're looking for before you start putting in numbers. All right, so that's what we're looking to do. Oh, by the way, I should have said this before, just pause at any time, like pause in the beginning, solve it yourself. Pause now, solve it yourself, and come back and look and see, did you do it correctly? So we have this situation, we know these two things, we can plug those numbers in, and we get this, 0.2853, right? You divide these, so that tells us that the ratio of acetate to acetic acid in our final solution is 0.2853. Right, I just wrote that out here, 0.2853 moles of acetate per 1 mole of acetic acid. Written another way, because we can sum that up, 0.2853 moles of acetate per 1.2853 moles of them combined. This is important because all of the acetate and acetic acid comes from the solution that you're adding. It comes from that glacial acetic acid that they're asking you about. So yes, OH minus, the hydroxide, is going to create the acetate when you add the acetic acid. So acetate comes from the acetic acid. I know maybe saying too much. So your answer in the end has to account for both of these things. It's how much acetic acid needs to be added, but also how much acetate needs to be there as well. I'm going to pause this now, and I'm going to solve it sort of out of board space. And so you could do the same thing. You could create the solution now and take a look at the next video for